Yeah, hi, so I'm Tom. I'm talking about grain size distribution, its impact on the mobility of analog pyroclastic density currents and the deposit of these currents. To start off, we're going to do a bit of an introduction to sort of what PDCs are and why we should care about this sort of thing. So you can see in the graph from Dane to Hubert that if we ignore the extraterrestrial ones because gravity has an impact here on avalanches, there's a clear relationship that volcanic sort of avalanches are much more mobile than these non-volcanic avalanches, so have much higher run-out distance over height. So then we need to look at these volcanic ones because they're more mobile and examine why they're so mobile. So it's been suggested that there's a range of reasons, including the topography, the aeration of the flow with gases, and these gases can be brought in from fracturing of clasts, burning of organic material, or just entrainment of air as they flow, and things like the mass as well as the actual charge. So then within these flows, the actual fluidization method has been proposed by a few different things, and Sparks suggested in 1976 that this is because of the fines that lubricate the flow. So if we see here in these photos, you can see there's a range of grain sizes in the deposits of PDCs. So this one on the left, as you're looking at it here, is a large clast in an ignimbrite deposit in Snowdonia. Whereas if you look in the other image, this is from Almeria in Spain, and we can see really clear fine crystals and ash. So there's a big range of grain size we need to examine, and then these have an impact on mobility. So then to examine these, we can't actually look at the pyroclastic density currents, we use analogue experiments. So then we've created these series of research aims. So we wanted to investigate how the grain size distribution, especially these fines, impacts the run-out distance, the velocity, and then how this is recorded in the deposits. So then we decided we're going to use this analogue method, it's been used in previous experiments by Smith et al. And Rowley et al. So we wanted to use this setup, and it's a 46-degree impingement ramp to encourage propagation of the flow along a 1-degree flume. So there is some transport, but we don't have material running out the end and losing any deposit we might record. So then to simulate the material properties we see in natural PDCs, we're using basal gas aeration from compressed air. And this has been kept consistent, so we're not having to consider the impact of gas supply in the mobility. So then the materials we use, we made this a suite of analogue mixes, because previous work has used monodispersed and biodispersed currents in a 3D flume like this setup, or they've used polydispersed mixtures in a 2D flume, but this doesn't allow for us to look at the deposits and other features that we're quite interested in. So we used a monodispersed mix of 45 to 90 micrometers to use as our kind of base control, as this has been used previously, so we had some good comparisons. And then we created a series of 5 mixes based around different proportions of between 45 and 750 micrometer particles of glass Ballatini beads. So by changing these mixtures, we could look at the impact of percentage of fines within, so whether we had 80%, 45 to 90, 90% or 100%, and we could also look at the actual sorting parameter, so how we were classifying these materials based on the different proportions and the range of grain sizes present. Starting off here with the results, and we thought first the key mobility feature we want to look at is the run-out distance of PDCs. So if we look and plot run-out distance against proportion of fines, you can see there is a bit of a trend, but there's not much. When you're at 90% of fines, there's this huge range of results. So you can see there's a slight increase if you go from 80 to 85 and kind of to 90. You can see in some cases there's an increase in the run-out distance. So it's suggesting that the percentage of fines does have an impact on this run-out distance. But then when we compare to sorting parameter, we see a much clearer trend here, where the more better sorted currents, the lower values, have a greater run-out distance, and these more poorly sorted currents which are heading up towards 1, except with this final value here, the most poorly sorted current has a higher run-out distance than the slightly better sorted ones would fall. And this could be due to impacts of sorting effects like percolation happening. So we know in these grains we've used the same density throughout, so we can say it's not a density-driven process causing this. So it's possible that in this most poorly sorted, we have a lot of potential for things like percolation to happen, which is allowing a fine base to form, which then allows the flow to propagate much further. But in general, we're saying that the flows with more fines, especially well sorted, running out further because they have more energy, because there's less energy lost due to interparticle collisions during percolation and the other sorting effects we're seeing. And the second aspect of the mobility we want to consider is the velocity. So we start off with the kind of bulk velocity and see here there isn't much of a trend between them. So straight away we're thinking the percentage of fines maybe doesn't have much control over the bulk velocity of the current, and you can see kind of the error bar as well here, suggesting there's not really anything. So again, we apply sorting parameter, and again we're seeing a trend appear, and it's a bit more noisy. There's a lot more variation in the values here, but we can see in general as the current gets more poorly sorted, the velocity decreases. And this is probably because there is interparticle collisions as poorly sorted currents propagate, and the particles can fall into interparticle voids and percolate downwards, and then you have fluidization from below that pushes the fines up, because the finest particles fluidize much more easily than the slightly larger particles. So they're moving back up, and we're having cycles within the current. So we're seeing lots of energy loss to interparticle collisions here, I think. So then if we look at the actual flow front, we get a bit of variation, and there's kind of variations in this. Video won't play, but it's if it was going to play, you can see me later. I've got a YouTube playlist of all the videos to watch, and you can see basically as it propagates, we have these pulsatory behaviours where different packages of material come along and mix, and there are variations in the acceleration as this happens. And you can see basically in each graph the amount of variation changes, and actually I suspect here that this is more to do with the sorting parameter than it is the actual proportion of fines, because we're seeing like lots of variation. So in the quad disperse and the tri disperse, so in these cases these are much more variable as they propagate along the flume than the monodisperse and bidisperse. So it's not the sorting parameter here, I suspect it's actually the proportion of fines. So then we want to look at the deposits. So if we compare to previous work by Smith et al, he created a suite of phase diagrams to use to interpret the deposits of these flows. And we can see here that our results don't really map onto these phase diagrams. Now, I suspect this is because the work of Smith used a monodisperse current, whereas these are all polydisperse currents. So we suspect this is why it's happening. And this is probably because there's a surface roughness, there's lots of different particles, which are allowing for deposition at higher velocities. It could also be due to experimental design, where Smith et al. Used a waxing current, whereas this experiment used more of a constant, so we didn't just end the current, as it were. So it could also be due to setting within the current and the time. So there's a few variations in experimental setup here that actually could be causing the variation in phase diagrams more than anything in the actual results. But then if we look at the deposits as well in the bed forms, we kind of identified 4 key bed forms here. So elongate, lunate, cross-stratified, and asymmetrical cross-stratified. And there wasn't much variation between any of the current types in what bed forms we had present. So I suspect that actually the bed forms present may be related to other things other than grain size. because there wasn't much control. But there were some interesting features came up in this that maybe have more wider scale impact. So we can compare here to some field deposits in Ecuador. And if you start by looking at these are elongate beds in the field. And the elongates are now as the basal deposits, the bottom here, they're thin laminated beds. Now the key feature is these were posed in the field to form on high angle slopes, whereas in our flume it's forming on a 1 degree slope. So this could be because also the field deposits are dilute current deposits, whereas ours is a dense granular current. So it's possible that these deposits and bed forms aren't actually only possible in dilute, it can also form in dense granular currents. And this could have an impact on the slope angle that they form on. And then again, if we look at lunate, you can see this is the main base deposit in ours. And again, in Ecuador in the field. And they're forming very similar shape, and this is how we've identified them off morphology. And again, these are interpreted as dilute current deposits, and these are appearing in dense granular current deposits. So it suggests that maybe the bed form type present isn't as indicative of current conditions as we thought in terms of being dilute or dense. And the final one that's interesting to talk about is these asymmetrical cross-stratified, as we've called them, or they can be called sometimes interpreted as shoot and pool in the literature. So they're identified here in red in our deposits, and we've got Lachaise and in Oregon. So we can see here that all of our currents are supercritical, so there is no granular jump occurring, which suggests that they're actually forming due to the build-up of previous bed forms below, creating a blockage which they're propagating over. And that's similar to the idea proposed by Brand and Clark, based on these deposits in Oregon. So to conclude, we had three main conclusions on the mobility. So grain size distribution and the initial current sorting both impact the run-out distance and the velocity. But the initial current sorting is more important than the percentage of fines in controlling the run-out distance and the velocity. And then the percentage of fines seems to be more important than the actual current sorting in this non-uniformity of the current, in how much we're having lateral variations in velocity as it propagates. And then one final point we had was this unsteadiness appearing, or calling unsteadiness in pulsatory behaviour. And these are auto-generating at points along the flume. And we suspect because this is a single release into the flume, it's not an impact of release from the hopper. And this could be a feature of the current. But we haven't been able to investigate this properly, and it needs further work because this is a 1-year Masters by Research project. So it didn't have enough time or scope to investigate this, but it's something we should look at in the future. So thank you for listening. Any questions?